Good. So thank you very much for the kind introduction and for the invitation. I'll be very happy to talk about joint work with John Leo, Francesco De Anna, and Jan-Erik Sulzbach. We've been studying the Cahn-Hilliard equations with temperature. So the idea is that we want to extend the Cahn-Hilliard equations with an evolution equation for the temperature. The question is, what kind of equation should we add? And so this is like a modeling question. And then in the second part, I will also talk about some analytical results. To give you some kind of overview, so like the Cahn-Hilliard equations, as you saw also earlier in this conference, is like a system of equations that describes phase separation. It goes back to seminal work by Cahn and Hilliard in the 50s. And so this describes the process of phase separation. And so what we do have or can think of is like that we have a binary fluid. And this fluid wants to spontaneously separate. And in each of the separated phases, sort of parts, the system would have like a pure component. And this is described with a phase field, which is denoted by phi. And this phase field can take values between plus and minus 1. So I guess many of you are familiar with this, and this phi equals plus or minus 1, we would call this like the pure phases of the material. There's many classical works on the Cahn-Hilliard equation. I've just quoted a few. And then there's also some work on the temperature-dependent case for the Cahn-Hilliard system. So Cahn-Hilliard in 1989 and 1990 has first derived the models where he combined or coupled the Cahn-Hilliard equation and the heat equation for the temperature. And so here we had studied several applications, and there has been also numerics on this. So there's also like quite some literature. And Alt and Pavlov in 1992 sort of had a different approach using the Ginzburg-Landau theory of phase separation, and they combined this with some kind of thermodynamic theory for non-equilibrium situations. Then in 2005, Will and Schimperner also discussed the temperature-dependent case, and they started from a theory that is based on microforces, and then this was like extending the model by Alt and Pavlov. And there have been also like some analytical works. So like in last year, Maurecchio published a work on the existence of weak solutions and on entropy solutions for a system related to the one derived by Will and Schimperner. And the talk today, if you like to have more details, just kind of have a look at this preprint. We want to study again the temperature-dependent case for the Cahn-Hilliard system. And we aim of deriving the model based on thermodynamic principles. And I would like to explain this in more detail. Let me first think a little bit about the physics that we have somehow in mind for this system. So as you saw earlier, and which is like typical, like for the free energy, like we would have a term which contains on the one hand like a term which is like the mixing or the interfacial term. And moreover, we have a term which we want to call W of phi, which you can think of as a double Wahl potential. The parameter epsilon here is related to the thickness of the interface. Again, so we have this diffuse interface models, and this epsilon is a parameter that is related to the thickness of this interface. And what we would sort of find natural is to say that at high temperatures, the mixing term should dominate. We would have more mixing of the two phases. And for low temperatures, we would rather think of that we have more separation into these two pure phases. Therefore, we would say the term W, which is the double Wahl energy potential, that this should sort of dominate. And having said this, it's very, very natural, obvious, to let this parameter epsilon depend on temperature, and this is what we will do also in the following. Moreover, what we would also like to do is like part of the modeling that this double Wald potential should be there at, let's say, room temperature, normal temperature, but at high temperature, we would rather expect this to become a single Wald potential. You will see, I will come back to this later. The model framework is, on the one hand, classical irreversible thermodynamics, where which goes back to Onsager, and the idea is somehow that if we think of the continuum, then that we are somehow close to a local thermodynamic equilibrium state at every material point. And there's irreversible processes going on, which lead to thermodynamic fluxes. Moreover, we follow the so-called energetic variational approach, where we start from I have an energy dissipation law, a least action principle, Newton's force balance law. I will come back to this also later. So this is somehow the principles that guide us and that we take sort of as the starting point. Let me first talk about the kinematics. Like in this continuum frameworks, we need to have some kinematics, some transport. And for the phase field function, we assume the continuity equation that you see here. So we have here the continuity equation for the phase field function, where u denotes the velocity of the material. This is sort of standard. What is not standard or debated is the question, how does the velocity or the related flow affect the temperature? What is the interaction, so to speak, between temperature and the flow? How is the temperature transported? And to our knowledge, this has not been solved. There's not a unique answer. And in this talk and also in our preprint article, we focus on these two different assumptions, A1 and A2. So in the assumption A1, we assume that the temperature field moves along the flow map. When is this interesting? We will later consider the action functional and look at the variation of the action functional with respect to the flow map. And we need to know what happens to the temperature. And in this assumption A1, we say, okay, the temperature field is transported along the flow map. In the second hypothesis, we would say that the temperature is not affected by the velocity or like the flow map. It's just like a background field. The temperature is just given independent of what the flow of the material does. And so therefore, this is sort of saying that U represents uniquely the dynamics of the mixture of the two phases, phi in plus and minus 1. Yeah, so there's no effect on the evolution of the temperature. This is like the second assumption. And of course, they could also think of mixtures of like a combination of the variants A1 and A2, so that in the end you could have like infinitely many combinations, infinitely many models derived. But here we want to focus on A1 and A2. And in particular, I will show them in the later part of my talk that for the system that we derive under the assumption A2, so where we have like the temperature as a background field, that we also have existence of solutions, whereas we don't have this for this model derived under the assumption A1. Yeah, that's fine. In order to do all this thermodynamics and the energetic variational approach, we need to have a free energy, and the free energy of the system, we now take this as the starting point. Here you see the terms that I discussed earlier. We have the W here as the double Wald potential. We have here the interfacial energy that tries to avoid the mixing. And we have the factors in front. Earlier it was just the epsilon, and now and the 1 over epsilon, and now we let this parameter that sort of is related to the thickness of the interface, we let this parameter depend on the temperature theta. Moreover, we want to allow that this double Wald potential can be somehow modified when the temperature is increasing. And this is where we somehow did like a simple assumption on this form. Yes, so that this bulk energy W of phi and theta is of this form, double Wall potential plus a polynomial in phi, just phi squared, multiplied by a factor C of theta, so that the function depending on the temperature. The idea is again that at high temperatures we could have like a potential which has just a single minimum, whereas at low temperature we are thinking of having a double Wall potential. So like the epsilon tilde of theta is a positive increasing function. What we will assume later, also in analysis, is that it is of this shape, the simplest shape, epsilon times theta, for some material parameter epsilon bigger than 0. And similarly, we have a specific assumption later in the analysis part of this function C of theta, which is just this polynomial, where theta bar is like a critical temperature. You could think of this as the temperature, for instance, where the potential has a transition from a double Wall structure to a single Wall structure. And then moreover, this last part is a typical part that you might maybe know even from other work on the Cahn-Hilliard equations. We have just like the Boltzmann constant times temperature times the logarithm of the temperature, which is due to a caloric part of the free energy. So this energy is the starting point of the derivation that we use for deriving the chemical potential. Chemical potential, just the variation of this free energy with respect to the phase field. This is just the derivation, so you get this formula. Similarly, the entropy we can obtain by looking at the derivative of the free energy with respect to the temperature. So therefore, we have the chemical potential and the entropy derived. Moreover, from the least action principle, we get also more insights. As the action functional, we again take the free energy here. We integrate over our domain in the Eulerian coordinates. This is like related maybe to Martin Krusic's talk, yeah, where he was talking about Lagrangian Eulerian coordinates. So this is like related to this. So we have the free energy here and as the integrand of our action functional, and we want to consider this as a function of the flow map. And so then we just derive the variation of this flow map, the variation of the action function with respect to the flow map. And this then is equal to this integral over the conservative forces times delta x. So now the assumption on the temperature enters. You see here I have item I and item 2i. If I assume that the temperature is transported along the flow map, we obtain after several calculations that the conservative force in this term, in this case, is given by the phase field times the gradient of the chemical potential plus the entropy times the gradient of the phase field. If, however, the temperature is just determined by the background, or like a background field, so like as we described in assumption A2, then the conservative force is just given by phi times nabla of the chemical potential. So here you can really see the difference, how there's different assumptions on the temperature enter into the model. Then there is a dissipation principle that we consider here. And so that we have this Ansatz here for this dissipation, where we have this some friction parameter eta depending on the phase field and the temperature times the velocity squared. And this term here is more like due to mathematical contributions. So we add another dissipation term here. And then the force balance says that all the dissipative terms, which we obtain here by looking at the variation of the dissipation with respect to the velocity, that these dissipative forces plus the conservative forces add up to 0. And then putting all this together, we obtain that the flow map how shall I? Sort of like if we assume that the velocity really is given by a flow map, is generated by a flow map, and that we have sort of like assumption on this friction coefficient which enters into the dissipation, then we have again two cases. Assumption A1 on the temperature yields this evolution equation for the phase field, and if the temperature satisfies the other assumption, we obtain this one. We can rewrite these, I mean, just like plugging things in. So like you can see here that we have the phi squared u. So you just somehow divide by phi, divide this equation by phi, solve for u times u, phi times u, and plug this in here. And then you obtain this blue formula, this one here, as the evolution equation for the phase field under the assumption A1. Similarly, if we take these two equations that we obtained from the variational approach, plug this one into this one, then we obtain this equation as the evolution equation for the phase field. So what we see here is if we compare these two, is they are the same except for this term here. And here you already see some mathematical difficulty showing up, which is why I want to address this at this point. So the phase field function phi is a function that takes values between -1 and +1. And in particular, at the interface, it can be equal to 0. So this causes trouble in this fraction here. In fact, this is why we were not able to prove existence of solutions. One would probably have to look for dissipative solutions, some kind of measure-valued solution. But then, on the other hand, we went over to the other model where we have the assumption A2 and then obtain this evolution equation. And for this one, in fact, we can prove existence of classical solutions. And somehow this term here is like the reason why the different mathematical difficulties occur. In order to have a thermodynamically consisting model, we also look at the entropy and entropy production. We want to have like the first and second law of thermodynamics being satisfied. There's maybe too many technical details also in here, so don't worry about the formula. So the message of this slide is maybe written here in the bottom. We can obtain the total energy of the system is conserved. So we have that the first law of thermodynamics is satisfied. We also make sure that the Clausius-Duhem inequality is satisfied. So we also have the second law of thermodynamics. This gives some more equations that we can put together. So if I now write all these equations for the system satisfying the assumption A2, if I write this down, so this was like the assumption where we say that the temperature is transported according to like some kind of background field. And then we obtain this system of equation as like the Cahn-Hilliard equation with temperature. So first of all, we have an evolution equation for the phase field function. And secondly, we have an evolution equation for the temperature. And so what you can see here on the left-hand side, this is all linear terms and phi. And on the right-hand side, we put together, you see here the definition, we put together the non-linearities that we obtain just from the derivation using this energetical variation framework and the thermodynamics. Similarly, for the temperature equation, so like the parts on the left-hand side are the linear contributions, and on the right-hand side, we have to deal with various non-linearities. Again, I think the details are not that important for this talk, so I will not discuss this more. What we want to, but I would like to give you some idea about the theorem that we have for this model and like a little bit ideas about the proof. So like so I want to show you that we can prove existence of classical solutions, in fact uniqueness, as well for this model A2 that we obtained. But we will show this for small time and under a smallness condition related to the initial data. So like this equation, and then here, equation 6, this inequality here is like the smallest condition that we have to impose. Phi0, let this be initial condition in the space B d over 2 plus 2. This is a Bezoff space, and we used here the Bezoff spaces, not the Sobolev spaces, because this yields like better a priori estimates that we need for the nonlinearities. And so that we make use of the little Pauli decomposition and the Fourier analysis to get these a priori estimates. So this turned out to be useful, but this also means, I have not said this before, that we work on the whole domain. So we work on RD, this D being bigger or equal to 1. So the physical case, of course, would be 2 or 3. So we assume that the Phi0 is in this Bezoff space, and also like that the initial condition is in the Bezoff space minus a theta bar. And the theta bar is a positive constant temperature, like a critical temperature, if you like, some special temperature. The smallest condition now goes as follows. So we want to assume that there exists a small constant epsilon 0. This will show up here on the right-hand side. Moreover, on the right-hand side, we have the minimum of 1 and some material parameters that are in the model, and the Boltzmann constant. And then we have on the left-hand side, we have this parameter epsilon, which is related to the thickness of the interface. We have the Laplacian of Phi0, and then we have here the 1 over theta bar times the maximum of 1 and 1 over epsilon, which will become large if epsilon is small, obviously. And we have here some contribution from the initial data of the phase field. And over here, we have a contribution which should be small, which is saying that the theta 0, the initial condition, should be close to this theta bar. The smallest condition goes as follows. We assume this says that there exists a small constant, epsilon 0, such that for any epsilon and theta bar, the following inequality holds true. And this is sort of like this condition here. So now this condition here is somehow saying that the theta bar should be large. And this somehow indicates that the theta 0 also needs to be large. So this is some kind of restriction here. But however, that's simply coming out of the technical part of the proof. Good. So let me state the main result. Under the smallest assumption I've just said, and for sufficiently small time t bigger than 0, this system that I presented before admits a unique classical solution on 0t times Rd on the whole space. And it belongs to this function space of continuous functions in time, and then being in this Bezoff space Bd half plus 2. And the temperature, again, has the same regularity as the initial condition, and is continuous in time. And due to this parabolic structure that we have, we can even get better regularities for the phase field as well as for the temperature, phase field and temperature. So the sketch of the proof goes as follows. We're following like a fixed point argument. And for this, we do the following Ansatz. We assume that the phase field function can be written as the function phi r plus a delta phi, and this function phi r is just solve this equation where we set the right and right side to be equal to 0. Yeah, otherwise it's the same equation that I had above. And similarly for the temperature, we do the Ansatz that the theta can be written as the theta bar that you know from the smallest condition plus sort of a perturbation delta theta. And having this Ansatz, what we want to show is that we can write these remaining nonlinear partial differential equations, that we can rewrite this, that we can discuss this, and we want to show that this nonlinear partial differential equation that we obtain has a solution. And this we do with a fixed point argument. And for this, we introduce an appropriate function space, and the appropriate function space for these additional terms delta phi and delta theta It's just, I mean, given that I didn't put the technical details, the essence is these functions should belong to the function spaces that are written in the theorem. And moreover, we assume that we are in a ball of radius chi. This is written here, where the norm that we have defined there is somehow related again to this function spaces in the theorem. So we have this space, which is like a compact convex space. And we now want to define a suitable continuous operator on this space and want to show that it is a mapping from kappa chi t to kappa chi t. Oops, sorry, there is this question marks. This is just the equation of the PDE. So for the, now we have to define this operator. Again, this is technical details I don't want to discuss here at length, just to give you an idea. So that we define this linear operator by putting these functions delta phi and delta theta on the right-hand side here. And then we ask whether this operator somehow has sort of where this delta phi tilde, delta theta tilde is the solution of this system here. And if we have this, then we can find the fixed point. How do we do this? We do this by showing that this element here, in fact, is again in this space. I'm sorry, now we have all these question marks. I'm sorry, they were not there earlier, so but I must have compiled it too often. So the solution still belongs to the space that I have defined. And so we have, and we obtain this due to the smallness condition. So this is somehow where we need the smallness condition that I introduced earlier. And we also make use of the fact that the time t is sufficiently small. And then we can apply Schauder's fixed point theorem to get existence of the fixed point. And then we can also prove uniqueness by showing that this operator L is in fact a contraction with this constant here less than 1, which leads uniqueness of the fixed point, and thus the theorem, whereas the regularity follows from the parabolic structure. And all this then is based on the Little-Palit theory and this Fourier methods that we use them. So then we have this result that I stated earlier. We have the unique classical solutions of this model that we have here for the Cahn-Hilliard system with temperature under the assumption that the temperature is transformed according to the background field. So let me sum up. For this Cahn-Hilliard equation with temperature, we derived the models. This was an important part of our work, based on an energetic variational approach. We have discussed the issue about how to define the kinematic transport of the temperature, and thus in turn of the entropy. And so there's two cases we consider: that the temperature field moves along with the flow map, or it follows the background. And then, of course, we also have to deal with the thermodynamic conditions. So we have the Clausius-Stulheim relation fulfilled. We also have like the conservation of the total energy. Moreover, I showed that the model, which is based on the hypothesis A2, has a unique classical solution. And for details, I would like to refer to this preprint article. Thank you very much for your attention.
Thank you very much, Professor. So, questions? So, Professor Garke, please.
Yeah, first of all, thank you for the nice presentation. I have two questions. First of all, you had this parameter alpha. I did not see in your theorem whether alpha necessary was positive. So the differential operators look nice also without the alpha. The question is, can you also show something when alpha is equal to 0? And then a second question would be, you had a certain dissipation which leads to an entropy production rate. When you compare to the model of Alt and Pavlov, they also had let's say, a coupling between diffusive effects of chemical potentials and temperature. So this you would probably also be able to include if you choose your dissipation more generally.
So in fact, we like in the last section of our preprint article, we compare explicitly the existing literature with our model and derive also the models with the like in this framework. So maybe you might be interesting to have a look. It's now difficult to maybe to say this in wordings, but there is a relation, and you can between these systems.
Mm-hmm. So you can also have, let's say, gradients of chemical potential as appearing in the temperature equation and vice versa. Yeah. Because you choose a certain dissipation.
Let me. I was just looking for the alpha. So here you can see the alpha.
Mm-hmm. Yeah, for example, yeah, maybe even further down. So you have, or let's say in the linear, when you basically put the linear terms on the left-hand side, yeah. So you have, yeah,
like in this equation.
Yeah, maybe in 4, for example, yeah. I would guess. I mean, if you put alpha equal to 0, you still have a nice system. But in your theorem, you need.
We assume, yeah, we didn't consider, I would say, the case. I would have to think more about this. I mean, like here you see the gradient of the potential in there, of the chemical potential, but it's the gradient of mu squared. And I guess this is not what you had in mind, is it? Or is this the
No, I wanted the dissipation mechanism which you have. Yeah, okay, these are two different questions. So alpha being 0 is one question. The other question would be the dissipation mechanism. Yeah, I mean, you don't have, let's say, a coupling between the fluxes in the two equations. So, but we're probably taking more general dissipative functionals. You probably will be able to.
And the power, yes, I think so too. Yes, and here of course we try to keep it simple. So here you can see maybe a bit more about.
Yeah, maybe then. Okay, sorry. That is really what I mean. So in some models you also have, let's say, gradient of chemical potentials multiplied by gradient of theta, and the overall you would need to have a positive definite bilinear form in these variables. Okay, but this is probably possible by having more general entropy production rate. So this is like a model of Alt and Pavlov they consider.
I will have another look, but thank you.
So thank you very much. So Professor Richter.
Yes, I wonder if you had a chance to look at the long time asymptotic behavior.
So far, we are not able to, because we really need to assume that we have small time. So we assume that we just have existence for sufficiently small time.
Oh, I see.
And we need this for like proving this. That the solution that we have here for our continuous operator, that this is again an element of the space, and then we use that this t is sufficiently small.
Oh, I see. So you don't have a long time behavior yet.
Yeah, exactly. Yeah.
Okay, thanks.
Thank you very much. So Professor Pater.
Yeah, I have a very quick question. Do you know what happens if you substitute the Fourier heat law with some other laws, for instance, with the Maxwell-Cattaneo law?
In principle, I guess this will be possible, but I haven't calculated this.
But do you think it would be more difficult, or because you see the equation would become hyperbolic, the second equation? Well, I'm just wondering.
I mean, there's two issues. One issue is deriving the model, and the other issue then is to prove existence of solutions.
No, exactly. I was wondering, because usually when you use the Fourier law, it's the easiest to handle. Sometimes when you change the heat law, there are some difficulties which come into the picture. Sometimes the difficulties are, let's say, of the same level, but sometimes it's a completely different story. That's why I was asking.
No, thank you. But that's, I mean, as I already explained, also for this temperature dependent with the transport, it's changing. And then that's, I mean, it's just that we don't know how to deal with the system in the classical sense, like big sense. And we don't have big solutions probably, but I mean, of course, one could then start doing the dissipative solutions. But yeah, it changes a lot. Thank you.
Thank you. So we have last question. So Professor Gracelli.
Thank you. No, I was wondering, I mean, here you use a particular functional framework, right, which it seems to me forces you to consider the whole domain, I mean, the whole space, okay? Have you considered the possibility of overcome this weakness somehow of the theoretical result in order to consider bounded domains?
In fact, also, Jan-Erik Sulzbach, one of my co-authors, had started to work also on considering dynamic boundary conditions. So this is then also like related to work by Howard Garke, and then to include this into the system. I guess, I mean, I think there's many more things we can do starting from this approach. And I'd be happy. So if you or others have like, I mean, specific suggestions what to study next, please don't hesitate to contact me.
Okay, thank you.
So we thank again Professor Schlömerkemper